Hi, hello everyone. In this video, we are going to see about the DC power transmission in a HVDC system. So, in a HVDC system, full control over a power transmitted can be done. Then the ability to enhance the trans and dynamic stabilities can be made. Then fast control to limit a fault current in a DC lines, like by using HSS, high speed switches, breakers. Then stability limitations. So normally the AC power transfer is depends on a angle difference between the voltage phases. So when angle increases, the maximum power transfer will get reduced in a AC system. But in DC it is a long distance DC power, and also it is a constant. uh, then voltage control. So in a AC system requires more reactive power, like inductive or capacitive loads for long lines. But in DC station, the reactive power will be needed according to their loading levels. So normally for running the line itself, we don't need a separate reactive power as like a AC system. So next, line compensation. The AC line requires a shunt and series compensations in long distance transmissions. Mainly is to overcome this line charging, and which means the starting current and the stability limitations. So in AC system, it is possible by using a SVS, static VA, or compensations or static VA systems. So next, interconnections of a AC line. So different frequency AC lines, it's very complicated to connect a different frequency AC lines. So the power level and the frequency signal should be same for connecting a AC line in a type A, which means normally we use in substation system schemes as a one out of scheme. Even after interconnecting a two AC different AC lines, there will be a large power oscillations and increasing transient disturbance, causing both lines to get tripped. So to overcome this, we use a DC link to connect a two different AC system. So it will be a controlling power flow, and also in addition to that, asynchronous DC link we are using means we don't need any coordinations for controlling the signals. We don't need such a kind of things as like AC. So next, ground impedance in a AC system, ground or zero sequence current cannot be permitted in a steady state due to the high magnitude ground impedance, which results in a disturbance in a power transfer and also causing a telephonic interference. So, but in a DC system, ground impedance, it is negligible for the DC current and DC links. And with reference to a ground, we can run a pole, like we can mentioning it as a monopole, which means a single pole operations that can be made through a DC. Next, energy availability. So this is the formula to find the energy availability. 100 into 1 minus equivalent outage time divided by a total time. It is mentioned in a percentage. Then transient reliability. So the transient reliability, to find it, we need to use this formula: 100 into number of times HVDC system performed divided by the number of recordable associated AC line faults. So these are all the technical parameters what we see is in HVDC. Then coming up to the topic, types of HVDC link. Normally we have a three links. One is monopole link, second one bipolar, and third one is homopole links. So monopole link, it is a single conductor of a negative polarity and uses the earth or sea for a return path of a current. Sometimes the metallic return is used as a return path. Then in monopole link, two converters are placed at two different stations. Mainly we use a negative polarity in order to have a less Carnot effect. Obviously if you are using the earth as a return part means there will be a several small disadvantages because of using the earth as a return path. So this is the basic structural diagrams of your monopole link. Here we have a one generating stations, then AC power in the sense the transformer which converter transformer which is used for supplying the power to the converters. So the converter station what I have said, converter station 1 is at one end and the converter station 2 is at other end. Converter station 1 which converts a AC to DC, then converter station 2 which converts a AC to DC to AC. And this transmission line can be made as per the required kilometers or required distance, and the individual earthing for both the converters are been given below. And this earthing can be made with keeping some distance from our converter station like 15 to 55 kilometers surroundings. We will make this earthing stations. And for earthing mostly we might use electrode kind of materials for earthing the monopole stations. Next is your bipole link. This is the commonly used HVDC links in our substations. So the bipole link has a two conductors. One is positive and second one is your negative, and also uh, neutral as a earth. Then the link has a converter station at each ends, which means separate two converter stations at each ends will be provided and with the midpoints earthed through electrodes. If any pole got tripped due to fault means automatically the link will get changed to a monopole and supplies the power as per the monopole level. So in this way we can have a continuous power flow without whenever there is an interruption in one link, and other link can be used independently. So this is your bipole link overview structures. Here we have a AC system. The transformer converter transformer we use as a star star and star delta transformers, and in a converter one end we use as a rectifier and converter two end you use as a inverter, vice versa the same. Then in between the midpoint we has a earthing point where the electrodes will be connected in earth rods. So the HVDC line connecting the one station and the another station, uh, it is having a two lines. One is positive polarity line and second one is your negative polarity DC transmission lines. So whenever the uh, converter 1 and 2 is running and there is any fault persisting means automatically one link or one line will get isolated and another line will run with a monopole power level, and earth will be taken as a reference for grounding in order to complete that full circle or a return path. So this is your bipole link in HVDC. Next coming up to the monopole link. So the monopole links are same as like a bipole link, but in here the both the conductors or the both the converters are used in the same polarity. Either it is a positive polarity or it is a negative polarity, and always operates with the earth or metallic return as the same like bipole level. In homopole we use the same polarity links. Instead of a different polarity links we use the same polarity rings. So this is your structure of your homopolar link. In here the same as like a bipole links, the AC station which is comprised of your converter transformer, one is star star and star delta level. Station comprised of two converters and other station comprised of two converters. In between we use this earth link as a midpoint. In here the both the lines are in a negative polarity, which means the same polarity we are using for transmissions. Nowadays homopolar links are rarely used due to their inefficient power flowing level. So normally Converter comprises of 6 pulse converters or 12 pulse converters, then transformers, which means the converter transformers used for supplying the AC supply to the converters, then smoothing reactors, which is connected in the DC yard after converting the AC to DC or DC to AC. The smoothing reactors will be get connected. Then the DC filter for reducing the harmonics of DC. Then tuned AC filters and HVAC filters in order to supply the reactive power and also reducing the harmonics level of your AC system, which is getting converter going to get supplied to your DC supply, so which means HVDC stations. So this is your basic overview structure of your HVDC. In here, the one indication is for your 12 pulse converters, two indication is for your converter transformer, which is star star and star delta converters transformers. Then third one is your smoothing reactor, which is comes after your converters, pulse converters. Then the DC filters, which is connected parallel to your DC lines. Then tuned AC filter and HVAC filters in order to reduce the AC harmonics and also supplies the reactive power to the AC system. So this is the basic structures of your HVDC system. So coming to the main equipment, converter unit. uh, in here we use a two three-phase converter bridge, which forms a 12 pulse converters, which means two sets of converters per pole per phase will be connected. In this way we use a two 6 pulse converters as a 12 pulse converter. Then the valve can be packed as a single or double or a quadri valve. The upcoming diagram you can able to see that each valves are used to switch in a segment of a AC voltage forms. Usually valves are cooled by air, oil or water. Mostly we in nowadays we use a liquid cooling using deionized or demineralized waters. Usually valves designs are such a kind of module, like each module of valves will be containing a series of thyristors, like a few thyristors will be combined in a series to form a module. Likewise there will be a modular structures, and total modular structures will forms a one valve, full valves actually. Next, coming to the working of valves, the valve firing signals are generated in the converter control at a ground potential and are transmitted to the thyristors by optical cables. Uh, then the light signal which received at the thyristor level is converted to a electrical signal using a gate drive amplifiers with pulse transformers. Then the valves are further get triggered and supplies the DC supply. And also these valves are protected by our snubber circuits. Firing protections can be made, and also a gapless surge arrestor is provided in order to overcome the higher surge or transients. So this is the connections diagram of your valves. In here we use a star star and star delta transformers for supplying the AC supply to the valves. And single valve is that there are different types of connections, as I said, a single valve, double valve and quadri valve. Each valve comprises of a modular designs of a series of thyristors, which means set of thyristors will get connected in a series, and then it will forms a single valve. So likewise in a single valve we have a set of number of thyristors. Next is your converter transformer. So the converter transformer comprises of a different types as per your phase or winding level. Here we use three phase two winding or a single phase three winding or a single phase two winding transformers for supplying the DC sorry AC supply to the converters. So the primary side is connected in parallel with neutral grounding, and the valve side or the secondary side is connected in a star or a delta formation with a neutral ungrounding. The converter transformer is designed to withstand the DC voltage stress and eddy current losses due to the harmonic currents. So next is your filters. In here we use a AC filter, then DC filter and high frequency filters. So AC filter is a passive circuit which provides a low impedance path and a shunt path for the AC harmonic currents, and also used for that supplying of a AC active powers. In order to supply the active power as much as we need a reactive power also in order to push them, so we use this AC filters. Then DC filter, same as like in a DC yard DC line which transfers to the other station. In between or the in parallel to the DC line we use this DC filter in order to eradicate the harmonics in the DC. Then high frequency filters. So normally these high frequency filters are mostly seen in between your AC bus and your converter transformer portion, or sometimes in the DC bus and DC filter areas. So mostly these high frequency filters are used to suppress the high frequency current flowing in your line. So next, smoothing reactors. A smoothing reactor is a large series of a linear reactor which is used to smooth the DC current. Then DC breakers. So the DC breaker, normally the AC breaker and DC breaker, there is a difference between both. Uh, the DC breaker is a another type of arc quenching technique actually. The AC breaker, normally during a zero crossing we use it to break the uh, current level, because at the zero crossing level the level energy dissipation will be very less. So but in DC that is not possible at all. So in order to break that higher level of current and voltage, we need a set of a separate parallel connecting LC filters or LC circuit in the breaker. This parallel connecting LC circuit, which is responsible for creating an artificial zero crossing level, and also helpful in breaking the DC current and voltage without any damage in our breaker DC breakers. So the following are required in your DC breakers. One is creation of a artificial zero crossing. Second one is dissipation of a stored energy inside the LC circuit, which is connected in a parallel to the DC breaker. Then withstanding the voltage between the uh, contacts, and also prevention of arc restrikings. So these are all the main elements in your HVDC station. Coming back to the overview of your HVDC station. So this is your overview of your HVDC station, how it works. So in here we use the bipole structures which comprises of your monopole level also. So uh, the AC line or AC bus which is connecting with your converter transformer star star and star delta converter transformer. Further it supplies the AC supply to your 12 pulse converter. Now I am considering a single monopole level, that will be a ditto for your another monopole. So after it is connected to your 12 pulse converter, it will the thyristors will get triggered and DC supply will be produced by converting AC to a DC. Then it will move on to your DC reactors, which is your smoothing reactor. Then DC arresters are placed uh, after the DC reactors. So in order to overcome the surges or transients, we use this DC arresters. Then your DC filter areas where the DC harmonics get suppressed in the DC filter, which is connected parallel to your main pole bus and your neutral bus. Then your damping circuit will also get connected in parallel with your stations, which means your pole and the neutral buses. Then DC surge capacitor and also the DC line arresters will also get connected in the line of your DC line after getting a tuned smooth DC. So this same set of a DC line uh, will goes to your another station, other end of your station, where we use this same kind of connections, and then that will convert your AC DC to AC. So vice versa, we can use in the power flow level, which means either it can be used in a forward direction or it can be used in a reverse direction. It's upon our operations. So these are all the main structural overview of your HVDC stations. Hope you understand. I think so. See you next video. Have a nice day. Nandri vanakkam.